They decided to put the Norwegians together. So here comes another Norwegian presentation. I don't have any Norwegian landscape pictures in my slide. So here's my background picture, and we'll get started. My name is Bjorn Vardal, and I work for IBM, the J9VM team. Same team as Dan, who presented earlier. My past projects, I worked with the team for 2 years, and I've worked a little bit on some of the DSR 292s on method handles and on Lambda. And now I work mostly on the Valhalla project. And today's topic that I will cover is debuggable runtimes. This thing, don't trust me. So back to debuggable runtimes. So when I find it very useful when I develop to be able to effectively debug my runtime, implementing a prototype and it didn't go as I expected. Instead of digging through my code again, I can actually use the debugging features that are already in the JVM to figure out what I did wrong. Of course, there's also defects. They come in all the time. To solve a defect, I would mostly work on a VM defect, but we also do triage work where which component does this defect actually belong to? Is it a JIT issue? Is it a garbage collector issue or whatever? And it's nice to have tools for that too, where you can say, or we can very quickly figure out where does this bug actually reside. So yeah, so the point there is to instrument your JVM so that you can avoid recompilation where you even just to activate some build flags for a couple of reasons. One thing is that recompiling can actually hide your issue. So you thought you see a problem, you just need to activate some debugging tools, and you recompile and suddenly it doesn't show up anymore. Or it's actually a deployed production system, so you don't want to tell your customer says, oh, I have a problem, and you're like, okay, could you stop everything you're doing, and here's the new VM and our JVM. I just want you to run that and watch the world break again so that I can fix it for you. So obviously, it's valuable to have good instrumented, a debuggable runtime. So what do I want you to take away from this presentation? I want you to get a structured understanding of the features of a debuggable runtime. So this is not, hey, we did something new, or that kind of like new development presentation. It's what have we done over several years, and where are we? Some points about where we are now. Because the thing is, we talk about this. It's not that actually that hard to build a runtime, to build a language runtime, build an interpreter. You throw it together. It might not be able to do everything, but the thing is, it needs to be serviceable. If you want anyone to use it, it needs to be serviceable. That doesn't, like, for us, that might mean pushing it to a customer. It might mean you using it within your own company. Nobody's going to use it if the moment you hit a bug, you can't help them. So what I will do in this presentation, I will look at some debugging practices. Basically, the theoretical approach to what should you do when you debug. Then we will translate those into debugging features. What should your JVM or any language runtime be able to do from a debugging perspective? And then I will talk a little bit, or maybe a lot, about the J9 solutions that basically how the implementations of those features in the J9. So what do we do as debuggers? It's definitely not an exact science, and it's different from any kind of system. And it doesn't only apply to software either. We debug hardware as well, right? I forgot the book I wanted to show you, but anyway, I had this this book given to me by David Aggins. It's basically an attempt to provide some generic guidelines for debugging. And he made a list of 9 points. I won't go through them all, but some interesting points. First, he said you have to understand the system. way too many bugs are caused by insufficient knowledge or incorrect assumptions about how it was supposed to work. You need to be able to make it fail, as in, if you know about an issue, you need to be able to make it appear on demand. Quit thinking and look. So you can make up many theories about what the issue might be, but there could be code and data that tells you that actually you can just forget about this theory. That's not it. So quit thinking and look. Divide and conquer. So basically confirm whether behavior is correct at a certain time or when you exclude certain features. And the list goes on. And yeah, and they're all good points, but there are really 4 of these that I believe depend on some degree of system support. So those are the ones I will branch out from here. So make it fail. You have intermittent failures. You keep rerunning it, but if it's intermittent, you have no idea when it's going to appear again, right? So you need some way of increasing the failure rate. Or decreasing it, or making it go away. It's also valid. Quit thinking and look. Stop making up theories. Look at the data. It requires that there's data to look at and that there's a practical way to look at the data. Divide and conquer. You need to be target specific, so when you run it again, you either need to confirm that the issue is here or be able to confirm that the issue is not here. And changing one thing at a time is a 4th one here. You should avoid just saying, okay, let's go into debug mode. Suddenly you have to change your entire JVM and you have no idea, and maybe the issue went away, right? And you have no idea which debug feature actually turned it off, made it go away. So keeping those points in mind, what do they translate into? So I translate those 4 points into 4 features of debuggability. Not a one-to-one mapping, but here we go. Tuning, being able to change JVM behavior without changing the JVM. That means being able to turn optimizations on and off, changing policies, algorithms, the environment you run in, or in order to provoke bugs or just make the bug disappear. Next point is state. What did the application look at a specific time, right? That could be the time of a crash, it could be the time of the breakpoint, it could be a time of some other event like an exception was thrown. Okay, what did it look like? Then you have history. If you think about the way we probably all did it as students, but maybe a bit into career as well, printfs everywhere, right? You just see like what happened, and then, okay, next one didn't happen, okay, I know where I am. Of course, there are more sophisticated ways of doing that. There's also the way of doing history with multiple state snapshots, and the trade-off there, of course, is that yes, you can do that. You can say, give me a state, give me a state, give me a state. Sample rate is insanely low, and the amount of data is really, really high. So you end up with a trade-off between how much data, how often. And then there's analysis, which really is about understanding the state data, turning it into information. And it really, so that kind of turns it into or you could argue it's an extension of state, but I want to differentiate between obtaining state and reading state. So that's why it's the 4th point. So these 4 points is what we look at going forward. So let's connect them back to the practices. Tuning is about being able to change one thing at a time. It's about being able to make it fail. And it's about being able to being able to divide and conquer. So really, change one thing at a time so that you can make it fail, so that you can divide and conquer. History is about being able to quit thinking and look. It's about providing you with data, right? Same thing goes for state. And actually, same thing is true for analysis. They're quite closely connected. But yeah, so far. So where are we? We're back with the agenda. So far, we looked at the practices. We turned them into features. So now let's look at the J9 solutions. So each feature has an implementation in the J9 JVM, and most of this information is available online. If you Google the IBM Knowledge Center, you'll find most of this stuff. But let's get started with tuning. What have we done in J9 to be able to tune the JVM? It's tuning, not just switching, right? You don't want to just be able to switch on and off. We're talking about tuning knobs where you have a min setting and max setting. It might be on and off, but there's a lot of room in between. And there are a lot of knobs. So really you want a lot of resolution in each of these dimensions. How many knobs, how much resolution per knob, so you can focus your search. So let's look at how we have like what we've done in the JIT, in the GC, and in the VM to be able to tune. In the JIT, first one is really just the JIT on-off, which is exactly the kind of switch I was talking about on the last slide instead of a knob, but it gives a lot of power in divide and conquer, because if I get a defect in, and the first thing I would probably do is just like, okay, let's run this without the JIT and see what happens. Oh, it went away. JIT guys, this one is yours, and gone. I don't have to see it again anyway. The same thing goes for quick start and AOT, which, I mean, they're kind of our, yeah, you can do the same thing there where you just turn it off. But really, at that point, this becomes a JIT job, but they can keep going. You can change the invocation threshold, right? So you have a number of invocations you want to see before you JIT something, but then you have no idea when it actually happened, or you need to be able to control when this actually happened. Well, I can set the invocation threshold to 0 and say, I want you to always, I don't want you to run it, interpret it ever. Or set it really high so you never see it, but that's the same as turning it off. You can force the optimization level. So basically we have these levels, the cold, hot, or cold, warm, hot, very hot, and all that. We can force it to say, I want you to, so if you combine these, I want you to compile as, like, never run interpreter, go straight to the JIT, and I want you to run it as hot. So that way you can focus, say, I see this bug, I only see it every now and then, I never see it in the method every time, or I don't see it in the same method every time, so I suspect it might have something to do with the optimization level I'm running at. So you say, okay, I want to run it, always JIT it, always hot. Oh, look, it doesn't happen on any other level, so okay, I can focus the search into there. Limit file, basically being able to say, I only want you to compile these methods. You make a file with a list of methods and then say, from line 10 to 20, I only want you to do these methods. Rest of them, leave them interpreted. Or being able to say, I don't want you to compile this specific method. And also changing the number of compilation threads. Moving on to GC, of course there's, well, one thing to say about the GC first, or about the JIT. The JIT features are generally designed for debugging, right? You don't want necessarily the users to keep changing the way the JIT behaves. The GC is kind of in the other direction, where most of these features are actually designed for exactly that. The user should tweak, because how the GC should work differs from application to application. But it doesn't mean we can't use them for debugging, right? For example, the policy, being able to switch the policy so that, for the same reason as the user do it, right? But say, I see this garbage collection problem when I run one garbage collection policy versus another, right? Being able to change the size of your heap, right, is a good thing to do, because you get your out of memory. Was the out of memory because you actually have a problem, or is it because your heap just wasn't big enough, right? Same thing as with the JIT, you can change the number of threads that run, so you can see, is this a problem because I'm running parallel work, or, yeah. We also have some options for provoking dangling pointers to say, at this point, we have had, like, it's a likely point where I could end up with invalid pointers. I wanted to run a full GC at this point so that I can hopefully find those in my debugging setting and not out in the field. Turning to VM, similar to the GC in the way that most of the options are actually designed for to be used by the user, but can still be used for debugging purposes. One thing is when you run compressed references. If you're not familiar with it, it's when we're storing references to objects, classes, threads, and monitors as 32-bit bit values on 64-bit machines or in a 64-bit VM. So that we can use half the size for the references, and we just store them below the 4 gig line. But then being able to change the size of that area below the 4 gig line and not the, because if you basically end up with 2 heaps, right? So to change the heap size of that area specifically can also tell you a lot about, or being able to turn compressed references on or off. Again, a divide and conquer problem. Stack, initial size, increments, how much you incremented, specific to Java thread or OS threads. Being able to tweak these things can also tell you a lot about your problem. And of course, like I guess I could have mentioned that. The point is that all of these are available as command line options, right? So you don't have to go in and change some file and recompile it and see what happens. The point is to be able to quickly change JVM behavior without changing the JVM. We have different optimizations that happen, but in order to do performance analysis, we want to be able to deactivate or activate some non-deterministic factors. So there are some of those with spinning and scheduling tasks or threads. So this got very J9 specific. Most of these apply to us because of how we've done things and might not apply to other JVM implementations. But the point was to illustrate the level of detail required in order to change one thing at a time, focus your search that way, so that you can make it fail, find your problem, and thus divide and conquer. And again, to modify the JVM behavior without modifying the JVM. Move up the history. So the 2 points I want to talk about for history. One thing is where did your data come from? You need some way of, you need to instrument your JVM to give you that history data. And for long-lived applications, collection becomes a problem, right? You produce a lot of history when your JVM runs the same instance for maybe several months, and then that constant writing can also get expensive, even if it's not long-lived. And so basically your collection has to be efficient and cost-effective. So let's look at those sources first. One thing I already mentioned was the multiple consecutive states and just look at the difference between them, which is very expensive, has a really low sample rate, and tons of data that you probably maybe didn't even need. So is there a better way? Another thing is Health Center. Basically leaves you live it's for our JVM. We basically are able to feed out live information about how many threads you're running, how much memory you're using, CPU usage, and all of that stuff. But that is more, well, first of all, what happens when your application then, if it crashes, right? Or when the JVM crashes. When, not a great word there, but if your JVM crashes, what happens? Well, what happens is that the feed of data stops, and you have nothing to go on. So it's really great for looking at your applications, but not for looking at the JVM itself. And this whole thing is about making the JVM serviceable, not necessarily other applications. So then we have tracing, specifically JVM internal trace points. There are some other kinds of trace points as well. Application trace points, which is basically an API where we allow users to register trace points so they can use the same mechanism that we have for trace points for their trace points. And also the Java method trace points, which are basically, I want to know when I enter the Java method and when I exit a Java method, which can be very useful to align with the JVM trace points so you can see what JVM behavior maps to my Java behavior. So staying on the JVM topic, let's look at those internal JVM trace points. So as I mentioned, definitely not free, right? You're constantly registering trace points, and when you have, like, I think in our JVM at the moment, there's about 7,000 unique trace points that fire at different places, at least from the data I found. So what we want to be able to do is to control which trace points are active. So we can do that by, we have assigned them levels. So we can say, we're basically 0 is most important and 9 is least important. So it becomes this accumulative thing where you say, I want level 5, and it only activates trace points that have level between 0 and 5. Of course, then we have to determine this when we write the trace points, which we write into our code directly, into our JVM code. And we have to determine at that point what level do we want this trace point to have. We can also do it by component. For example, in our port library or in our memory management, I only want the trace points from one of those. Also individual IDs for each trace point, being able to say, I only want these specific trace points from the port library. So just a quick example of what JVM tracing could look like, because there's a lot of talk about what it is, but you don't actually, or how it could be, but not what it actually looks like. So basically, we just we put in the timestamp, the thread ID, the trace ID, which is the trace point, the ID I talked on the previous slide. Event is, did I enter a code block? Did I exit a code block? Or was there some other event that I keep in track of? And then there's a data section. So the data section is the one that is designed individually for each trace point. So you give it a format string, and then you input your data into it. So in this case, I just took an example of when we look up a Java method. So what we see here first is only getting these trace points, I now know from this which method I was looking up, which class asked for it, where I can find the name and signature of the one I'm looking for, where we started our lookup, what kind of search method or algorithm I'm using, whatever is involved in visibility of the modifiers and what actually the result of the visibility check was, and in the end, what method did I get back. And all this, this information it could be valuable on its own, but it's also, it can help me improve debugging when I use a native debugger. I can use all of these, I can look in my trace points and find that, I want to look at one of these classes, I want to look at one of these methods or whatever I want to look at. And also use it in other debuggers, in our JVM debugger, which I will get to later. And then we have the collection that I mentioned earlier, which is important because, we don't want something that wasn't supposed to be noticeable suddenly become very noticeable because you're collecting way too much history. So we have our memory buffers. We have trace buffers where we put the data from our trace points. And it's not only one stream of trace points. It's every thread will need their own. Unless you want to put in some kind of concurrency control, you need each thread to have their own buffer. And you probably don't want to introduce that concurrency mechanism because, again, you don't want to notice this feature and it could slow it down. So how can we keep the memory usage down? First, yes, it's per thread. And we want to keep the memory usage down. And when you think about it, when an error occurs, what do you actually need? Do you really need all the data, like all the history from when you started the application? Because if you think about it this way, how long can your JVM stay in a corrupt state without crashing? Probably not for a very long time. At least that's some assumption I'm making. So then that means you can wrap your buffers. So you can reuse the same memory over and over again. So only the most recent, which is also the most relevant history, is the only history you have. And it also means that the buffer size is known always, because you can specify how much memory you want to use, and it's just going to keep wrapping through it. So I have some more information on outputting this, like the output formats of this of the history. But some of that information also applies to state. So I will first move on to state, and then get back to the output. So looking at state, so it's a snapshot of the process at a certain time. And I want to talk about the formats of like our different formats that we provide, and also when and how you can get these snapshots. So looking at formats, we have our Java core, which from what I see is similar to hotspots HS underscore PID something, which is a human readable file. It's a human readable file, and in the Java core, I didn't see that in the hotspot version, but it's parsable in the sense that what we have done is added a line code for every line, so you can actually easily find every line of a certain type. For example, you want to see all the memory segments that were allocated, and you just search for the code for memory segments, and there you go. So that means you can change the format. It means you can change the format of the actual data, but the actual line, but as long as the code stays the same, you can still find them. Platform independent kind of follows from the human readable. Point is, it's text. And what information is in it? A lot of useful information. What happened? Why did I end up with this Java core? Did I segfault? Did I actually ask for this one? Or yeah. The JVM version, very useful in the divide and conquer world when you want to see when we run our tests and you say, okay, it failed here. Yesterday it didn't. What code went in, right? So then in your Java core, you can easily see the version of it. You can see the user arguments that were used when you ran that specific one. So we're back to the tuning. You can see the specific tuning that applied in the fail state, and not what is different when it didn't fail. System variables, a lot of time what can happen is the user didn't realize that he had something in an environment variable, like IBM Java options, which is basically a way of putting something in a system variable or environment variable, so that I have it apply as user arguments or command line options for the JVM. They forgot one was in there and they can't understand the behavior. Is that a question?
Just a quick question. Is that parsability a supported feature? Because I mean, in theory, everything's parsable.
Yeah.
It's a standard format that you support.
So yeah, I get what you're saying. I'm not sure about the actual that list of actual codes. Codes is a published list that these you can expect. But the point is that just because someone added a space and you didn't expect that, when you like if you look at how the hotspot file looks, it's completely formatted just for readability. And the point here is it's more formatted also for parsability, so that you can see a line and you see the code, and I don't know whether you can expect that code to always be the same, but at least it's not going to be a simple thing as someone changed the space further out and suddenly your parser doesn't work, right?
Structurally, you expect it to be consistent.
Yes.
There are tools that have been built against it that do parse it and pick out various parts of the file.
So let's see, memory usage per JVM component is a very useful feature. You're looking at, you get an out of memory, right? And you can actually go into Java core and say, okay, I just want to do a quick check, like which component actually used all my memory. And it shows you, okay, the VM used this much, the JIT used this much, and the GC used this much, and then you can follow them in from there. See like what did the JCL use, and the different components. Where did the memory go? A list of memory allocations, useful. Just being able. Then you have your code, your line code, where you can say, "Give me memory segments," and there you go. All the memory allocations are in there, so you can see the start address, end address, and different things there. Get the thread stacks, lock information, and all loaded classes per class loader. So a lot of information really quickly, very useful first stop for quit thinking and look. So quit thinking and look, I kind of split it up into having data to look at and having a way of looking at the data. Here you kind of have both, right? You get a lot of data and it's in a readable format. So system core, I mean, it's an OS feature, but we have added some value, as Orbit mentioned. Dan mentioned a little bit about it, but I'll talk about it a bit later. We've added some value that we'll get back to, and we also support the heap dump format for memory analysis. So getting to how do we get this, and that applies both to state and history. We have our dump agents. It's a command line option or a JVM command line option where you can say, I want a certain kind of dump, certain type, when something at certain triggers. So first the types. Stack and console are just output directly to your console, like very limited, some basic information about the thread states. System, Java, and heap are the ones I already mentioned on the previous slide. And JIT is that's diagnostic data for the JIT. And snap is those trace buffers I talked about. It's basically take a snapshot of the history buffer, the trace buffer, so that you can see, okay, what was the history at this point in time? So each dump agent is then triggered by a configurable event. So we have got a bunch of events. You can say, I want it at a seg fault. I want it at like when you start up shutdown. You can filter these because if I want to do some, for example, I want state information at the time when an exception was thrown, or not only when it was thrown. If it wasn't caught, I want a dump of some kind of state dump. And you can filter these like the exception. Which exception? If you put it on thrown and you get it on every time an exception is thrown, you're going to get quite a bit of data that you really didn't need. But like, if you look at, you can actually specify multiple of these. So a setup could then be that you want a heap dump on every GC, every full GC, and if you get an out of memory. And I want a system core if I seg fault, and I want a Java core when the JVM shuts down. And you started with that option, and like you will get your information when you need it. You didn't need to restart again and get everything to happen over. Try to get this error to occur over again. You run with dump agents activated that will give you the information you need. Just if you look at the bottom of the type list there, it's not really related to state or history, but it's an interesting thing where we can run a command line tool as a type when a certain event occurs. So you can, at VM startup, you can say, I want to run a profiler when it starts, or start health center when I start the JVM. Okay, so summing up those, tracing, basically all over the JVM. Trace points can be activated, deactivated. The data is stored in trace buffers, and buffer snapshots are available through the dump agents. We have a few other state formats, ranging from basic thread info output to console, and to parsable files or human readable files to system cores. And we have the dump agents that will provide us those snapshots and are triggered by events like exceptions and signals. So, any questions? Okay, gonna move on. We're on the last point. So we will look at state analysis. So this is where we turn core data into information. So differentiating between those two. And that's, again, in order to be able to quit thinking and actually look at the data. I have two directions on this one. I mentioned earlier we added some value to the system core. So I will give you a little bit of detail about what we actually did there and how it helped us build a great debugging tool, which is a JVM aware debugger. And I want to show you how such a tool can be valuable. So, not dynamic dump reader, by the way, direct dump reader, is what Dan was talking about earlier, where we have actually, let's get the point up here first. We embedded a structure blob into the process image. So we said, basically the problem that has been discussed quite a bit today about taking taking the headers from our JVM implementation, extracting the information about the structure of information about the internal JVM structures, and then we load those into the process image so that if we end up with a system core, the information about the structures is actually in the core. So when we get a core dump, we can open it and pull it back out. So we have Java code that can read that structure blob and create a model of what the JVM looked like at the time of the crash. And then we have Java algorithms that can knows how to walk those structures, so we can do a stack walk, like a Java stack walk we have algorithms for that. It's similar, I think, Jeremy, I don't see him anymore, but, oh, there you go. You mentioned this about Google does something like that with basically informing GDB about how to walk the Java stack.
We're planning on doing the review, right? We're planning on trying to open source that soon.
Oh, okay. Yeah, so it's
when I saw this, I was like, oh yeah, you're right. It's similar.
Yeah, so it's similar to that, but it has a little bit more to it. One thing I want to mention though is that I don't want to trivialize the complexity of maintaining the structure information. I mean, some of it is.
Huge pain in the neck.
Yeah.
How big is it again? How many thousand lines of Python? A couple of thousand lines of Python.
Yeah. Okay. So it's definitely a problem that it's something to be aware of, that even though I'm talking about these features as, hey, look, this thing we did, you should probably do it too if you want to have a serviceable VM. It's not necessarily just, oh yeah, sure, do it. It takes some effort. But it's a great tool, is the point. So with this knowledge, we get this really powerful debugging tool that I have kind of hinted at a few times. But first, let's look at the native debuggers, what they actually, the difference between native debugger and what I'm talking about now. So you have native debuggers like GDB where you can explore a system core. Usually you require some source code and you require some debug symbols, and you kind of have to match your source code version to make sure you get that right. And then at that point, given this, and by the way, it's going to be platform specific as well. So given this, you can start exploring the JVM if you understand the complete, you have to understand the structure of it and know what to look for. A little bit on the understanding the system part. And you can, and also it's dependent on being able to find a suitable starting point. Usually that's not necessarily a problem to find, but you're sitting there with a core and you need to know quite a bit in order to get started. So if you look at DDR Interactive or jdmpview, which is the tool I've been talking about, so DDR comes with this API which we expose through an executable that we ship, and that's jdmpview. So because of that structure blob that I mentioned that is inside the core dump, we don't require any source code or debug symbols to do some certain operations. And we know a lot about the internal shape of the JVM just from the core file itself. And in the spirit of Java, it's backwards compatible, so cross version, so that we have version information, so you can read which way is it? You can read older cores on newer JVMs. It's also cross-platform, so I can read a Linux core on a Windows machine or using the Windows executable. and something else that is in the Java the spirit of Java, extensible. So because this is written in Java, we're able to, or not only because, but I mean, a nice feature of it being written in Java is that we can easily extend it. So our service team, they are able to write their own debug extensions on top of this tool. For example, one of them wrote just a quick check that he can run, a quick command where he says, is this class, I have a reference to a class, is that class in the shared class cache? So it's just a quick check, but it will tell you a lot about, oh, it wasn't, okay, so that's not the problem, right? So we also have the common errors some common errors can maybe be found programmatically. So if it's a known issue, you can program it out and say, I'm just going to run this on the core and check if that's the issue. One example of that is about a year ago, I was assigned a defect, and we seemed to be, when we did some shared memory, we had overlapping segments. So suddenly it was the end of one segment was later than the start of another one. And we're trying to figure out what was going on there. It turned out to be a Linux bug, which was fixed later. But the point is there that it's very easy then to use this tool. Just say, can you give me all, there's a command already for saying give me all allocated, like give me all the memory segments you have allocated. And then just run a quick scan on it to make sure there's no overlap. So if we got more bugs in where they say there's something wrong with my memory or something, or I just crashed, it takes 5 seconds to run this tool and say, oh yeah, that's a Linux bug, it's your Linux version. So I could say a lot more about DDR, and I think I already did say quite a bit about DDR. But let's take a look at it instead. And before I actually look at it, I'm just going to mention that these commands are not published, not supported. They are for internal J9 use, so basically the same as what the disclaimer said. Don't trust me on this. So let's just start quickly with something similar to GDB's info thread. And yeah, it's visible. So we get some quick info. We get the address of the Java thread or the VM thread, some thread ID and name of it. But also we get these suggestions. That's actually what the highlighting was supposed to map to. So the suggestions. J9 VM thread, you see it has an exclamation mark in front. It's actually a command. It tells me, and if you want to explore this further, here's the command you should probably use for it. The J9 VM thread command would be similar to it's kind of similar to GDB's print, where you know the structure of the shape of that thing, so you just say print this address as this type. Not that interesting for this, but another cool thing is being able to say the stack. Just give me the stack for this thread. And it knows how to, as we talked about, it knows how to read the Java stack. Because DDR knows how to read the stack. And yeah, this is a very minimal stack, so it doesn't contain that much information, but it does give me another suggestion. Do you want to look at the method? Yeah, sure, let's look at the method. So I get this method output, and it keeps giving me suggestions like, do you want to look at the constant pool, the J9 constant pool, or do you want to look at the bytecodes for this? Yeah, do you want to look at the bytecodes for this method, which is a really nice feature, especially when you have when you modify the bytecodes when you load them, right? So you can look at, you take the Java P output and tells you, in our case, for example, yeah, here's a method handle invoke or invoke exact, and that's not true when we load our bytecodes. We modify those bytecodes to be custom bytecodes. So then I can see all of those modifications because I can go in here and look at what do my bytecodes look at runtime. It's already getting a bit repetitive going through these, just stepping down. But let's just pick a different starting point and see other ways of doing this. DDR supports class for name. So I can run a class for name on a class, in this case test. And And it then, of course, suggests you can look at this class if you want. Say I want to know, did I hot swap this class? Did I do any class transformation? And oh, it turns out, yeah, we keep this field replace class. Yes, we did actually change. It seems to have been replaced. So useful information when I'm debugging, just knowing that, probably the reason why that cache I was keeping on some information in this class, the reason why it doesn't seem to apply anymore is because, it's not the same class anymore. Just one more, we have some analysis commands as well. Say a customer, they find this stuck Java application, and there's no obvious problems in their Java code, at least according to them. So they consider contacting our service team. And instead of doing that, first at least, they run the deadlock command. They just load that core that they got from that hung JVM, and they just run deadlock. Deadlock says, actually, there seems to be a deadlock loop between thread 5 and 6. Following that, look at, we see thread 5 and 6. Let's get the threads. And then we look at the stack for each of those to realize, that's where our deadlock is. It's in some customer code, and it's easy to find these deadlocks. Deadlock is, of course, just an example of one of these analysis commands you could run, but very easy to extend because you have all the information about the internal workings, the internal shapes and algorithms in the JVM. You can easily write extensions that makes it very debuggable. So conclusion, I think it's time for that. We wanted to be able to build a debuggable runtime. We based it on some debugging practices that we believed needed some system support in order to work properly. Turn those into debugging features to cover it completely. So have we covered all the practices? So we covered all the practices with features, and then we looked at these JNI implementations. We have the trace points, the core dumps, the dump agents to get those. We have DDR for analysis, and we have a bunch of command line options for tuning. And in case there's still any question about that, still don't trust me. Any questions? Yes?
So as I understand it, this is not publicly available.
Most of it was. I was only talking about the DDR.
I mean, the DDR is not.
Yeah, so DDR, it has published commands. Most of the ones I used here were not. Deadlock is. So that's why I used the customer story for that one. So most of these are not published. There is a tool that we now ship, which is IDDE, which can be installed as an Eclipse plugin that has similar commands. I don't think the output will look exactly the same. So they're not published as this. They're published, this is what we use internally, but they might be published as under similar names in IDDE, which uses the same, actually is based on jdmpview and uses DDR. Yes?
You also use the tuning flags in your regression test?
Tuning flags in regression test.
The JVM crashes, you have a regression test that lists the crash, the bugs are there, trigger the tuning flag.
Yeah, so I believe the answer is yes. At least Dan is nodding. I'm not sure. I can't point specifically like where we would do that, but definitely just for the way. Or Dan, do you want to say anything about it?
Yeah, we've got our test system. We run our tests under all the different modes. If we find particular bugs, we find enforcement, the GC of I, GC others, all of those kinds of things.
Yeah, I was going to say that, but I wasn't sure if Dan wanted me to. Okay. Another question?
Can you describe the DDR again, what it is and what it's,
Let's see, just.
how you get it?
So yeah, it's kind of part of that whole discussion that has been going on today. Where was that? It requires that whole question we talked about today about how do I take my headers from my native JVM code and turn it into something I can read in Java, right? So we have a mechanism for it. But it's the reason why it doesn't necessarily apply to what we've been talking about here today is that this mechanism is limited to our JVM, right? We can make a lot of assumptions that wouldn't apply to the whole space of all code that we would like to be able to interrupt with, right? So we have code that knows how to read those headers and has sufficient knowledge about the JVM to be able to turn that into some structure information. Then when we start a JVM, we take that structure information and we load it into our process image. And then if I run a dump agent later on to get a core file, that core file is then that's my complete memory, including that shape information. Then when I start DDR Interactive or jdmpview, when I load this core dump, I know where to look for this shape information, which means I can explore my core in terms of, in the context of that shape information. Is that?
So you're reading in these headers from the JVM.
Yeah.
And from that, I mean, what is it that the DDR knows about the structure?
It knows the shape of, for example, what we call internally an object, a JNON object or a JNON class. Okay. It knows the structure of what those looks like. What those would look like, and then we'll be able to use that information to say, well, if you're saying that there is an object at this location, then I can give you that data in terms of what an object looks like, right?
And you get that information from the headers, or is there some information written into Java code that helps?
So the Java code knows how to read the information about the information we loaded into the core. It started from the headers, from the JVM. We processed it and turned it into something we can read using Java code. And then the Java code is instrumented to know, or we program that to know how to use that information to run its algorithms. I think Brian wants to end this.
Well, yeah, I don't want to take up the whole break, but I was just going to remind people that we have a break next, and so you can sort of set upon Bjorn, further as during the break.
Okay. Well.